I wanted to start thanking Koushik, Arka, and Subinoy for this kind of invitation, despite I making them very difficult find a schedule, because I've been away most of these days because of some personal reasons. But thank you very much for giving this opportunity. I've been attending some of the talks, but on and off, not really very regularly. But I thought you might be interested in sort of this new tool, using this new tool of gravitational observations as a potential probe of primordial black holes. And this is a very active field these days, and there have been many discussions in this meeting itself about how the merger rates of primordial black holes have already been used to constrain the abundance of subsolar primordial black holes, and also how the existing merger rates of more massive black holes to constrain primordial black holes in the tens of solar mass range. What I will be talking today is using the gravitational lensing of gravitational waves as a new potential probe of primordial black holes. This is sort of primarily based on this, and this is done with several collaborations. Many of them are here. Saumedhi is sort of sitting in the back row, and several other collaborators here. So since this is not exactly a gravitational wave audience, and you might not be following the details of what has happened in the field in the last 7 years or so, I thought I will very quickly give a quick intro of what has been happening in the field of gravitational observations. This one, all of you know, the first observation of gravitational waves directly passing through the Earth happened in 2015 by LIGO, and this was the observation of two massive black holes merging, each weighing about 30 solar mass or so. And since then, the LIGO and Virgo have observed order 100 compact binary coalescences over the last 3 observing runs. Most of them are binaries of black holes, double black holes, but there are also observations of double neutron stars and mixed binaries of a black hole and a neutron star also. This is sort of a cartoon way of representing the masses of these compact objects observed by gravitational observations. This is the vertical axis, is the mass of these objects in solar masses. The horizontal axis has no meaning. So all of these blue dots are the gravitational wave black holes. So for example, the first cluster means this is produced by the merger of 2 black holes, each weighing about 25 to 40 solar masses, forming a much more massive and rapidly rotating black hole of about 60 solar mass or so. And the more massive ones are touching even order 150 solar mass, the merger remnant. And you can see that in contrast, these crimson black holes are the black holes from our own galaxy observed by X-ray observations. So you're seeing clearly these extragalactic populations of black holes are not really representative of the black holes or the black holes in our own galaxy are not representative of the extragalactic black holes that is being uncovered by these observations. These orange dots are the neutron stars observed by gravitational observations in comparison to the radio pulsars in yellow. There are these strange objects which are half blue and half orange, and currently we are unable to ascertain the exact nature of these compact objects purely from gravitational observations, because we do not have enough sensitivity to measure any imprints of the material of the neutron star, for example, tidal deformation, etc. So currently all this classification is based on the measured mass of these compact objects, and this is a peculiar mass range which could be occupied both by neutron stars or black holes. So we don't have a way of asserting their nature yet, but future observations with better signal-to-noise ratio, we will be able to measure the tidal deformation of these neutron stars through their imprint on the gravitational wave signal, and perhaps even to measure the other post-merger oscillations, etc., and hence to classify them more accurately, more reliably. It's sort of it's a very quick summary of some of the highlights from the gravitational observations. We know that these were the first observations of merging black holes and merging double black hole systems and merging black hole neutron star systems. There is these observations uncovered the existence of these heavy mass black holes that was sort of a surprise to many astronomers. Black holes, stellar mass black holes of heavier than about 30 solar mass or so. There is a potential evidence of intermediate mass black hole, in particular this very short signal called GW 190521. And if we believe our data analysis method and GR as a theoretical model, this must have produced an intermediate mass black hole of about 150 solar mass. So, and everyone knows about the dramatic multi-messenger observation of this particular neutron star merger, GW 170817, which was not only observed in gravitational waves, but was observed across the spectrum of electromagnetic waves, starting from gamma rays all the way up to radio, and produced a remarkable amount of science. There are a couple of putative neutron star, double neutron stars, or black hole neutron star binaries. We have not seen any electromagnetic counterparts from them. So this classification is based on their mass. There is this very peculiar object which was seen from this particular gravitational signal, GW 190814, which hosts either the heaviest neutron star or the lightest black hole that we have seen in the history of astronomy. These observations have provided a really nice way of testing the validity of GR in the regime of extreme gravity and extreme velocities. Just to give you a context, just before merging, these compact objects must be traveling at speeds close to the speed of light. They have this extremely massive and compact objects moving at speed of light and colliding. They are these sort of cosmic particle colliders. And if we expect any deviations from GR, this is sort of one regime where we hope to see. But so far, all the data has been consistent with the predictions of GR. But you don't know, in the future, with better precision of the measurement, some deviations from the prediction of GR might show up. These neutron star observations, in particular, these multi-messenger observations, have provided new avenues for cosmography. We have a measurement of the Hubble constant, which is very imprecise, but with a large number of upcoming observations, and some of them having electromagnetic counterparts. This precision of this Hubble constant measurement and perhaps measurement of other cosmological parameters would improve. Also, this is when I was giving the same talk a couple of weeks before, Arka reminded me that this is not really the only interesting science in cosmology one could do, because the power of the gravitational observations is it provides a direct way of measuring the luminosity distance. And if we can associate them with electromagnetic counterparts, and if we measure the redshift from electromagnetic observations, that gives a very good way of measuring the peculiar velocity of these objects also. So there are interesting GR effects that we have seen, the evidence of higher multipoles, binaries with large mass ratio. We know that gravitational radiation is quadrupolar in leading order, but we do expect higher order multipoles of the radiation, and we have seen imprints of this in the data from some of the high mass ratio binaries. And the electromagnetic observations that follow this GW 170817 have provided some very interesting, tantalizing hints of the origin of heavy elements in the universe. In fact, there are reasons to believe that a large fraction of the heavy elements in the universe are produced in neutron star mergers like these 170817. It must have happened in millions of years. So we are also looking at starting the population properties of black holes. We have black holes and other compact objects. We have ordered 100 observations now. So we are starting to infer some of the properties, like the mass function of black holes. There is a potential imprint of the pair instability supernova mass gap in the mass spectrum, which is yet to be verified and confirmed using upcoming observations, etc. And it also have provided interesting surprises. For example, it turns out that most of the black holes that LIGO and Virgo have seen either have very low spins or have large misaligned spins. This was again a surprise because if you were to trust the measurements of the black hole spin in our own galaxy using X-ray observations, they all produced, or a good fraction of them have supposed to have large spins. So this was also a surprise, and it is clearly not a selection effect, because if at all, we are biased towards highly spinning black holes because they would produce louder and louder gravitational waves. So there are elements that we do not understand yet in the black hole formation scenarios that produce these gravitational signals. Okay, and finally, this is only a beginning of the gravitational astronomy. The time volume, the space-time volume probed by these observations have been increasing consistently. And with even modest improvement in the sensitivity of these observatories, we are getting significant increase in the spatial volume that is probed by these observations, because gravitational waves detectors are really amplitude detectors, unlike optical telescopes. So if you increase sensitivity by a factor of 2, really the observable horizon will increase by a factor of 2. You get a factor of 8 in the volume of accessible universe. So the space-time volume probed by these observations have been increasing quite dramatically. And with the upcoming observing run, the O4, which will start middle of this year, we will be doubling or tripling the number of detections in the next order 1 a year. And there are plans to, at various stages of maturity and funding, to upgrade existing facilities. For example, the next upgrade of advanced LIGO is called A+, which is a couple of factors of 2 improvement sensitivity, which is already funded in the US with international collaborators. There are, again, there are fairly concrete proposals to upgrade the existing facilities to place better detectors in existing facilities, called A#, Voyager, etc., which would again increase the sensitivity by a factor of close to a half orders of magnitude, which will significantly improve the horizon of these observatories. And it is fair to say that in the next order decade or so, you'll be detecting thousands of gravitational signals. It's really opening up this new branch of astronomy. And there is also ongoing efforts in different parts of the world of thinking about the next generation observatories, called the 3G observatories, which will basically increase sensitivity by a factor of 10, which will make them to observe practically all the heavy mass black hole mergers happening in the universe in this sort of mass range of a few solar masses and above. So, the science case is quite diverse and strong. So there are interesting questions about the black hole astrophysics. How does nature form binary systems of black holes? What is the black hole mass function? Are these heavy black holes astrophysical black holes or primordial black holes? They provide interesting avenues of probing strong gravity, interesting tests of general relativity. One could also ask the question whether these are indeed black holes. Do we see any imprint of horizon, or in some alternative, like some surfaces, like are they fuzz balls or more an exotic ultra compact object? They provide interesting ways of probing the nuclear equation of state, because the tidal deformation of neutron stars in a binary system, when they are in close separations, provide imprints of the nuclear equation of state. And this is a very powerful way of probing the nuclear equation of state. There are interesting ways of probing cosmology using the standard cosmography techniques of standard sirens or clustering or lensing, etc. And there are, one also hopes to detect new phenomena. Again, certain things are guaranteed to happen. The detection of the astrophysical foreground of gravitational waves produced by a large number of mergers happening in different parts of the universe is bound to be detectable in the next few years. One hope, and it's again fairly certain that one would have some good chance of detecting this gravitational strong lensing of gravitational waves by galaxies and clusters of galaxies. Depending on the quadrupolar ellipticity of real neutron star, one hopes to detect neutron stars. And if we are lucky, a galactic supernova can happen in the next decade. That would be detectable. There are, it could be completely unknowns also. So among the sort of known knowns are the gravitational lensing of gravitational waves and the known unknowns. And if you look at lenses like galaxies, we can calculate the lensing probability or the lensing optical depth by using existing galactic surveys or comparing it with other high redshift sources like quasars. And it is fairly certain that when one does a calculation, one gets that the advanced LIGO detectors, there is 0.1% to 0.5% chance that one event be lensed. So out of all the events, order 0.1% to 0.5% of the events be strongly lensed by galaxies and clusters. So once we are in a regime where we're detecting hundreds of gravitational signals, we will be safely in the regime of detecting a handful of gravitationally strongly lensed gravitational waves. That is sort of going to happen almost certainly. There are more speculative but interesting effects. The gravitational observations also will enable us to probe a totally different regime of gravitational lensing, which involves wave optics. So if the lenses are, typically in all of the electromagnetic lensing, we approximate lensing using geometric optics because the wavelengths are very, very small as compared to any lensing object. But if the gravitational lenses have Schwarzschild radii of order a few hundred kilometers, which can happen in the case of stellar mass black holes or intermediate mass black holes or other compact objects, then the wavelength of gravitational waves are comparable to the length scale, gravitational length scale of the lensing object. So one can see very interesting wave optics effects such as diffraction and interference, which is sort of probably only can be probed using gravitational observations. And this offers a new way of probing primordial black holes. Am I? Okay. Right. So, this potentially provides a new way of probing, the existence of primordial black holes and the possibility of them forming a good fraction of dark matter. But since all of you know much better than me, this possibility is heavily constrained by a variety of observations. This is the exclusion plot of what fraction of the dark matter could be in the form of primordial black holes. As constrained by various observational probes. For example, this is from the lack of observation of subsolar mass black hole mergers observed in gravitational waves. This is the microlensing of light. This is the existence of some wide binaries, et cetera, et cetera. So this possibility is very heavily constrained, and I believe that currently the action is in this regime of theorists. But it turns out that with the current sensitivity of gravitational telescopes and the lensing is sensitive to sort of this region of a few tens of solar masses to a few hundred solar masses, and that possibility is certainly very heavily constrained. But even if the primordial black holes in this mass range forms only a small fraction of dark matter, they could have interesting other consequences. For example, they could serve as seeds of supermassive black holes. Also, it's a good idea to have multiple observational constraints because any observational constraint could suffer from systematic errors, and often come with various caveats. And there has been this episode of femto lensing of GRBs, and because certain systematics in their assumptions, this constraint has gone away. So, bottom line is it's good to have independent constraints. And this is what the idea is as your outreach graphic. The idea is essentially the same as the microlensing of constraints using light. You assume that you are in a bath of primordial black holes, and if there is a distant gravitational wave source that is propagating through space-time and reaching us, if a good fraction of the dark matter is in the form of primordial black holes, some of them could be scattered by these intervening black holes. And And when the mass of this lensing object is comparable to the wavelength of gravitational waves, you see this interesting wave optics effects. And the mass range, as far as the LIGO-Virgo frequency band is concerned, the corresponding mass range for lenses are order a few hundred to a few thousand solar masses. And then one would see interesting effects, just this interference and diffraction. So, well, again, one nice thing is that just like the gravitational waves from these compact binary mergers can be accurately modeled and parameterized by a small number of parameters, the lensing also can be modeled and parameterized in terms of a small number of parameters. Yeah. Working, Arun? Yes. Okay, sorry for the glitch. So it turns out that in a similar fashion, the lensing effect can also be modeled and parameterized. If we assume symbol lens models, for example, a point mass lens, which is a good approximation for such compact objects. So you can basically write the lensed waveform as a function in the Fourier domain as just a simple product of the unlensed waveform times some frequency-dependent magnification factor. The complex function. So the h of f is the original unlensed waveform, and lambda is a set of parameters that describe this waveforms, just the black holes, masses, spins, location, etc. And this is a frequency-dependent magnification introduced by this point mass lens. It's parameterized by the redshifted mass of the lens, m times 1 plus z, and an impact parameter which tells you what is the location of the source in the lens plane. And you can see that this is a sort of computed lensed waveform from a compact binary merger. So these unlensed waveform is shown by this gray chirp, which is a standard binary black hole chirp. And if you add a lensing effect by a 100 solar mass black hole, it is deviated to the red one, and you add a 1,000 solar mass lens effect. You can see this very interesting beating patterns. And one could search for these deformed waveform the data, and one could cast this in the Bayesian model selection problem. So given that the data D, you can ask the question whether a given signal is best supported by this lensing hypothesis HL or the unlensed hypothesis. So one could basically write down a likelihood for this lens waveform and marginalize over all the parameters. And similarly, you can compute the marginalized likelihood for the unlensed waveform. It's the standard marginal likelihood that you would use in the gravitational analysis. And if this base factor is significantly greater than 1, there is a potential evidence of lensing. So there is a simulation that shows how these, you can estimate all these 15 plus 2 dimensional parameters space posteriors. So this is of all the posteriors of a binary black hole signal. And if you were to zoom in, this is the corresponding parameters that describe the lens. So for example, this is a simulated lens waveform. So you recover the lens mass in this red cross, which is the estimated posteriors and the corresponding impact parameter. And one could, so we did a first search in the O1, O2 data a couple of years ago. And this shows these are the base factors, the log base factors that we obtained from all these order 10 events that were available in the O1, O2. None of them have a significant support towards lensing hypothesis. And this shows the marginalized posterior of the lens mass. So you can see that all of them have no particular support at any particular region. So they are broadly recovering the prior range also. And then this was repeated again by the LIGO-Virgo collaboration in the data from the O1, O2, and O3. Again, there is no conclusive evidence for lensing, the same kind of plot. So, and we also have analyzed the additional candidates that was discovered by the IIS group, and again found no particular evidence. So far, we do not see any of the events showing any significant evidence of lensing. But if there was a lensing effect, this is what we would have seen. Is sort of a comparison of a simulatory event with a unlensed signal and a lensed signal. So you would see a significant base factor supporting the lensing and a well-localized posterior for the lens mask. This is what one would hope to observe if there was a truly lensed signal in the data. Now, so for example, this shows a histogram of all the base factor in natural logarithms. So even if you see a distribution, but there is the largest value is order E. So there is no significant, none of these events provide a significant support towards lensing. Okay. So now we can try to use this non-observation of lensing signatures to put a constraint on the abundance of such objects in the universe. So, so one could use the approximate the event rate of the gravitational mergers as a post-quantum process with certain mean lambda, which we can estimate from the data. That's what we typically do. That's how we estimate the merger rate of binary black holes in local universe, etc. Similarly, we can also assume that the number of lens event is also follow a Poisson process, and the fact that we have observed a zero event, one can ask what is the what is the posterior of that Poisson rate of observing lens events, given that we have observed zero events, and that turns out to be this sort of exponentially falling distribution. And this is the rate, Poisson rate of the number of binary black holes observed during this last three observing run. This is only, in fact, only include the half of the third observing run. That's where you only see order 60 events. So this posterior peaks at around 60, while the number of, or the Poisson mean of the lensed events peak at 0. And you can calculate what is the fraction of the lensed events in the data, and that is 0 with some a fall off that goes up to order 0.1. So we can essentially say that with 90% confidence, we can say that the fraction of lensed events in the compact binary mergers happening in the local universe is at 90% confidence level, less than 0.08 or so. And this can be used to put an upper limit on the abundance of such objects in the local universe. So that we have to relate how this FDM, which is the fraction of dark matter in the form of compact object, to the number of lensed events or a fraction of lensed events. So that depends on our astrophysical model also. One has to assume a certain distribution, redshift distribution for binary black holes merging in the local universe. One has to assume a certain distribution for how these matches will be distributed in the universe, etc. So we use pretty simplistic assumptions. We assume that these primordial black holes are, at least in large scale, distributed uniformly in comoving volume. And as far as the distribution, redshift distribution of mergers, we assume different models which are inspired by population synthesis models or other considerations. So if you do that, one could do a simulation. So here is, for example, an example of how a few different distribution of the expected redshift distribution of compact binary mergers as a function of redshift. This is assuming a uniform in comoving volume. This is a particular population model, population synthesis model predicted by Dominic and Belchinski, and there are a few different models of primordial black hole mergers again in the literature. So what we just want to show that these sort of extreme models kind of bracket a range of possibilities. And similarly, if you assume that these lenses are distributed uniformly in comoving volume, you can compute the lensing optical depth. So using these simulations, one can actually calculate the fraction of expected fraction of lensed events as a function of the FDM parameter, the fraction of compact objects in the universe. And this can be used, I'll skip the details, to put an upper limit on the abundance of primordial black holes. This is the upper limit that we get currently. So this is a similar exclusion plot like the one that I've shown earlier. This is a mass of the primordial black holes from 100 to about 10 to the 5, and it's FDM. And and the constraints we can put again depends on our Bayesian priors. This is assuming 2 different priors for the this lensing rate, assuming uniform prior, and this is using a Jeffreys prior. So let's take the most conservative one. What we can rule out at the moment is that not more than about 80% of the dark matter could be primordial black holes in this mass range. It's an extremely boring and modest constraint, and in fact, it's already ruled out by other observations. But it provides a new way of making this constraint, doing this constraint. And as we observe more and more binary black holes in the future, these constraints would consistently improve. So here's a prediction of how these constraints would improve in the next few years. In fact, up to 2004, when we observe order a few hundred to a couple of thousand binary black hole events in the next few years, we will be able to put an FDM constraint of order into the -2, which is getting to the modestly interesting regime. But again, these observations, as I said, will not stop here. In the next few years, we will be continually observing thousands of binary black hole events. And if these next generation observatories come up, we'll be observing millions of them. So it really provides a new way of probing primordial black holes in this mass range, and which also would widen the mass range probed by these observations. So let me stop here and flashing the summary. I just want to make a couple of remarks also. There is an ongoing, more careful calculation of the bounds coming from the upcoming O3 lensing paper by the LIGO-Virgo collaboration. And we are also reformulating the method using a threshold independent way, which would make it a bit more robust. And one could also use the same idea to constrain primordial black holes of even higher masses. And here they will not produce these wave optics effects. These lensing would be in the geometric optics itself. But the fact that we have not observed any lensed even with small time delays can be used again to constrain these primordial black holes of millions to a billion solar masses. Let me stop here. Thank you very much.
Yeah, we have time for questions.
Yeah, regarding microlensing constraints, so basically when you assume that the lenses are primordial black holes, then does it not imply that the sources can also be primordial, like the binary black holes, which creates gravitational waves? So when you set those constraints, do you take that abundance also into account?
Not really, but so these are upper limits, right? So essentially you're saying that in the spatial volume that we are able to access, the abundance of dark matter, the fraction of dark matter in the form of primordial black holes is this much. And it doesn't rule out the possibility that the sources are can also be primordial black holes. Yeah, but typically you expect that only a smaller fraction of the isolated black holes become binaries.
I see. Okay, then it's fine. Right.
Okay. The next question is over there.
Yeah, I was just wondering if it's possible to constrain lighter mass PBHs also by considering multiple lensing events.
In principle, these lighter mass objects also introduce wave optics effects, even the single ones, but they will be weaker. So once we have better sensitivity, that I sort of briefly mentioned, that would increase the sort of bandwidth of our observations also. So once we have better sensitivity, we will be able to probe slightly lower mass black holes as lenses also. But I'm not sure if subsolar mass black holes would produce any measurable lensing effect that we can hope to measure even in the next 20 years. It'll be hard.
But do multiple lensing events, add up to give a...
Yeah, so in fact, if you want to look at this high mass objects, then multiple lensing would actually be important. In fact, Ankur Barsode, who is here, he is actually working on folding in the effect of multiple lensing, and because it has to be folded in when we need to make constraints on this high mass black.
Very nice
interesting talk. Have you looked also at the event rate and cross sections for lensing event by other lenses? I'm thinking about, for instance, stars in our galaxy, especially if you look in a certain direction, whether like in the bulge where the star density is very high, maybe even galaxies. I don't know if that works because
Yeah, galaxies, yeah, certainly people have that. That's most likely the first lenses that you would see.
okay.
And that is order with current sensitivity, that's order 0.1% to 0.5%
Of events.
of the all events. Yeah.
Okay.
Yeah. So we expect order 0.1% to 0.5% of all the LIGO events would be lensed by galaxies.
And these would be the geometric optics.
They will be geometric optics.
And stars in our
Stars, people have looked at it. I think Simon White has a paper on it. I think it's rather small.
Okay.
If your lens is a black hole and it has a QNM frequency, which is the same, similar to the gravitational wave frequency which is coming in, you expect a resonant absorption and emission, so some sort of a peak.
Yeah, so this is something we actually had looked at. One could think of in a more interesting scenario, right? If there is a cluster, like a nuclear cluster, a globular cluster, where there are many black holes close to the merger, and in principle, this one gravitational wave could perturb many black holes and produce a lot of secondary ringing. But if you look at just the simple numbers of the cross section, it's rather small. So in the case of this lensing scenario, it's absolutely negligible because the fraction of energy is absorbed by a single lens at large distances, very small. More plausible scenario is that we have a dense cluster with many black holes and a merger in between. Then one could, there is better hope, but it's still very difficult. But it's a very interesting idea. But we had actually thought about it. We probably will pursue it a bit more.
Thank you.
I think we can probably have one more question at the back there.
Yeah. I just want to understand this lensing process. So suppose I compare with the theory of weak lensing. There we understand that it is getting lensed because of the image is getting distorted. So how are you distinguish this in gravitational wave lensing, because you are not seeing an image, right?
Yeah, this is not really weak lensing here.
Okay.
It is closer to micro lensing. It's really, there is no real analog of this wave optics lensing in electromagnetic waves because you never encounter scenarios.
So basic signature will be this diffraction and interference.
Yeah, it is the diffraction imprint on the time series itself.
Okay.
We not look at images. You will never be able to make images of gravitational sources because the wavelengths are so large. So you measure time series very accurately, and this would introduce deviations in the time series signal.
Another question is that I read somewhere that the binary mergers that produce this gravitational wave, they can also source the generation of gravitational waves, right? So suppose these gravitational waves that are generated, they can also lens can they lens itself, or?
You mean the gravitational waves lensing themselves?
Yeah.
Yeah, there is a nonlinear effect, and that is already part of the calculation of the waveform.
Okay. But the effect will be very small, or?
So this is what you call a memory effect. Now the gravitational waves themselves, that memory effect, the gravitational waves themselves sourcing gravitational waves. There is called the tail effect, where the gravitational waves are scattered in the background curvature, which is contributed partly by the gravitational waves also. But that is part of the calculation of the gravitational waves.
Thank you.
Okay, so I think we should wrap up this session here. Let's thank the speaker again.
Thank you.
And we're going to go to the sort of more general discussion now. So, I mean, we can keep on asking questions to the speaker, Prof. Alexandra, from this morning. And you weren't able to join the discussion before. So if anyone's got more questions about primordial black holes in a general discussion as well, then, and now we've got Suradeep as well. So yeah, let's start the general discussion. So go ahead.
So my question is for Ajith sir. So you showed that double slit like pattern for the gravitational waves. Let's say we have two detectors. One is LIGO and other is, let's say, LISA in space. So what is the maximum difference in signal strength that you are like approximating at the present moment? So let's say if we are measuring signal strength maxima on the Earth and minima on the, like with the LISA, it will eventually have a waveform like pattern. So,
But these two detectors have operating in very different frequency ranges.
so then how do you plan to like measure that double
So
slit?
basically, what we are really going to measure is just what I showed in this time series data itself, right? Whatever diffraction, interference, etc., would change the shape of the gravitational signal.
So has this,
What you can imagine that like different these waves traveling at different paths will get different time delays due to lensing. So they're like different, like in a very naive way of thinking about that. You have different rays, they all get different time delays. So they beat together, and that's how we get these sort of beating patterns.
so has anyone performed this kind of calculation before? Like if I want to refer to some literature?
Yeah, this is precisely from a theoretical calculation. This is
Okay.
like the original paper is Takahashi and Nakamura, 2004 or something like that.
Okay, thank you.